So let us now solve a new problem with the script that I have provided. So in this session, we will see how we can evaluate equivalent springs under a rectangular foundation. This is a static 3D case. So this is a problem. Let us see. This is my PLAXIS 3D. I will have two cases. The one we're working on now is the static case. So I have here 40 kPa vertical stress. And if we see how many points I have for the springs, you will see now in a second. So what is the story of this spring constant? You must have heard about the subgrade coefficient of subgrade modulus. So let's go back to this. The coefficient of subgrade modulus in our geotechnical field. So basically, if you have a footing like this, so you can represent the soil underneath this area with equivalent spring. So this spring can give you the stiffness normally in the vertical direction, but you can also get the values of the spring constant in the horizontal direction. So we have here two orthogonal directions. Let's say this would be the x direction, and this would be the y direction, plus the z direction. So basically, all you need to do is to identify a point where you can have both the stress and displacement. So if I have the stress and displacement, so you divide the stress by the displacement, you get the subgrade modulus. This is the equivalent, because we are doing finite element analysis. And now, if you know that that each point here has this area, which is the area between the various points I'm considering, so I multiply this subgrade modulus by the area to give me the spring constant as force kilonewton per meter. The issue is, in PLAXIS, you don't get the stress and displacement from the same point. So if you see here, for example, if I go here, viewport, so these are the points that I have in this model. So let's increase. So I have identified here stress points, as you can see, but also very close to each point is a node. So the node will give you the displacement, and the stress point will give you the stress. So these points have to be very close to each other so that they can represent the stress and displacement at the same point. And this is why I have here, you can see here, I have those nodes I identified. You can go back to previous examples to see how we can do that. And also you have a stress point. So this node is very close to that stress point. The second one would be very close to the second one, and so on and so forth. So I have this distribution of the stress points and the nodes. This is basically a plan. So if we just remove the interface so that we can see it, so basically, so this is the footing, and this will be the distribution of the nodal points and the stress points. So basically what I have done here is, if I go to that, and I go to structure, and I see the vertical. So basically in this, I created, this is just a polygon. So I specified points here, the distance between the points, say 1 meter, okay? And the first pair would be half a meter from the edge. So I have several points here, node next to stress point, node next to stress point, so that the area served around each pair would be 1 meter square. You need to know the area beforehand. And it's a good idea to use like a regular distribution of this pair of nodes and the stress points. This is something you can control. So why you need to do that? Because you never know. If the structural engineer asks you to provide the spring stiffness under this footing, then you will be able to do that. You determine this and you extract it from the analysis, and then you give it to the structural engineer. And if you have, for example, pile draft where the soil itself is carrying part of the load and the piles carry another part of the load, so you should be able to see what happens and it's a change or communicate this equivalent springs to the structural engineer. So if you go back here, so I basically completed the analysis here. What do I have here? I have like 40 kPa, so this is pressure of 40 kPa, and basically we will see the results before we see how we can implement. So if I go here to the output, it will show me the deformation that we have. So I have just a settlement of a maximum of 3.7. This appears to be flexible footing because I don't have any plate or anything like that. So I already have the results. So this is what we need to query using our Python script to work out the stresses and the displacement under this footing at each pair. When I say pair, I'm talking about a yellow and red nodes and the stress points very close to each other, yellow and red. So this is what I mean by each pair. So the Python script will be able to extract these values and process it for us. So we will see how we can do this. So I would go to Expert, Python, Editor. You need to take note of that. Say Control Copy, and then Start Server, close. It will open for you. This is, we need a new one. So we need a footing. So let me just see here which one we are using under footing under static load. As you can see here, I have a multitude of those. So we need to check. This is a spring. This is for dynamic, and this is the one that we are after. Okay, I call it ChatGPT because we may train it later. So, and then you will have this actually in your model, in the material that you have. So we need to specify the desired phase. So if we go to this, so this is phase 0, this is phase 1. So we can specify here this is phase 1. If the password is different from yours, so this would be the one. And here there is an interesting thing. I am putting here some sort of boundaries so that the script can scan all pairs of nodes and the stress point. So, for example, if I go here, to the structure, I know. So, if you pick this one here, so you see the edge here starts from 8, end with 11, and also the Y would start with like 10 and go to 11. So for me, I can really put this one here, say, okay, this is just the boundary. You can put anything that you know that it will fall into this range. So from minus 10 to 20, and the minimum Y is also from minus 10 to 20. Let's check this one again because it's not minus. So I have to get this one right. So you can read the coordinates here somewhere. So at this point, so it's 8, and the X goes to about 11. So that's fine. So I can put here, actually, say this is from 6, doesn't matter, and this would be, say, 12. I know it will go through all of this. And if this point here, so the Y is between 8 and also 11. So I can go back to this, and I can say this is 6 to 11. If you are close enough, this should be fine. For the minimum Z and maximum Z, because the elevation of the stress points may not necessarily be the same. So my Z here is, you can see here, if I go to structure, my Z here is 0. So the stress points under the nodes will be underneath this. So I can say here, this would be between minus 0.2 and 0.2, for example. It should be picked happily. And then what else? Well, this is it. So it will go and retrieve sigma Z, sigma X, sigma Y. So you need to know which stress and which displacement you are interested in. So by default here, if we can see here, so it goes to UZ, so it's gonna get UZ for the displacement from the nodes, and it will get sigma Z, sigma X, sigma Y. So the input here has to specify actually which stress we are interested in. So let us see where this is in the script here. So because this actually, the script is actually designed to give you the three of them, to give you the X and the Y and the Z, so you don't have to do anything in this regard. So let us run this and see what we will be getting. The Excel file here does not change the name. You can change it here if you like, but the name would be results.xls, unlike the other ones. So I'm pressing F5 here, or to go to Tools, and then go to F5. So I press F5 here, and hopefully this will give us the results. So it may give us some error here. I know it will give us some error, for sure it will. Let us see. Yeah, we have some errors, and the reason being, if you read this carefully, well, we don't have enough comments here, but we can add a comment here, say make sure the output model is open. Okay, is open. So we can choose all of this, delete it just for clean, for a clean output, and then I can go here and I say, okay, give me the output model. If we go back to this, you see here, that the server port is 10,001, okay, because this is the output. We are interested in the output. So let us see if this will run or will have errors. We will see now. So apparently it hasn't been more than 11 seconds, and I have here some results. Let us see the results, and then we don't need this anymore. We don't have to save it. So let us see what we've got. We have date modified. So we should have now the results. It may be in a different, yeah, it's in a different. So I'll just put it in the folder here. So this is the results. It was at start at 3:14, which is pretty much what we have here in terms of the timer. So this is the script. So let us. The best way to do this is obviously to make sure that this is saved in the folder that we are interested in. So we save this one here. We can remove this one, and let us see if we run it again. If we run it again, so this file needs to be removed. Okay, and then we run it again. Hopefully it's not going to give us any error. So it has worked, and then now date modified. I have the results here, 315. This is 315. Well, you can add some features to work out the execution time, the starting time, etc. Let us open this. So these are the results. Remember, we are interested in the equivalent spring constant. So this is the node name. So we have 8 points. Why we have 8 points? Let us see if we have 8 points. So we could come here and we see how many points we have all in all. We have 9 points. So we have 1, 2, 3. 3 times 3 is 9 points, 9 pairs all in all. So so this count is 9, as you can see here. These are they are not necessarily in a sequence, so I have 9 points, and the stress points are the same. You have the coordinates x, y, and the z for each of those. Z is very small, as you can see, almost 0, and these are the nodes. And now these are the coordinates for the stress point x. This is a stress point y, and now we started to get, this is a vertical stress at each point, horizontal stress in the x direction, horizontal in the y direction, and then the equivalent force. This is just additional information. And guess what? Now we have this here. Actually, it's stress. It has not multiplied by the area because there is no input here for the area. Well, this is something that we can add. So I'll just take this back, and basically we are working with the upgrade modulus. All you need to do is you take each of those, and then you multiply by the area served between the various points, like this orange area here, which we know in this particular example is maybe about 1 meter. Like you see this here, it's 1 meter, like half a meter each side, so that's 1 meter. So basically, this how you can get the equivalent spring stiffness in any of the directions. And like I said, we can add to this the area somewhere in the code, but again, because I presume that you don't know Python programming, so for the time being, we are happy to live with the subgrid modulus in the vertical direction and also the equivalent in the horizontal direction. As you can see, this is a straightforward process. What we can try is basically to check the stresses at any of those. So let us see. We have the coordinates. So let us go back to this. Check the output to check that we are getting the correct results at the points we are talking about. So let us start with one of these points. So we have here. So we need the point. Let's say we need the point. Go back to this. We need the point that has 9.5 and 9.5. Okay, x 9.5. Okay, and the z is 0. Okay, so one way to do this is we can come here and take a horizontal section. What is the section? The elevation here is almost 0, minus 0.003. So minus 0.003, it's not going to make much difference. So minus 0.003, and say OK. So it will take a thin section. So this is a section. So we go view, and we see viewpoint here, and this will be the deformation. Okay, I'm interested in the stress. You can check whatever you like. So we need the Cartesian sigma dash zz. Okay, so this is how Cartesian zz distribution. Remember, we are interested in comparing at 9.5 and 9.5. Okay, the value we are getting for sigma zz, for example, from the is minus 40.6. Okay, they are all close to each other, to be honest. But let us see. So 9.5 and 9.5. So we can actually get this hint window, and then we keep changing. We need the 9.5 and 9.5. So you can see here, just read off what we are getting here. So this will be 9.5, 9.5, and we see sigma dash z, sigma dash z. So we need to bring this a bit down. We need to move. I'm just moving this laterally. So 9.5, 9.5, and we have something like close to 40 kPa, and the z is a bit smaller than this one here. Well, you can say that it's close enough. But let us see another point, the 8.46 and 8.5, because it's 41. Okay. Again, the elevation may not be helping much, but let us go back. We need 8.46 or 8.5. So 8.46 and 8.45. So 8.46. Sorry for the x. So x 84.6, and the y is 8.45. You can see the 41 is coming happily. Can you see this? Okay, so 41, we saw the 41 here for this. So the script is reading off the stresses correctly, and we may be in a position in the last session to show you how we can use this very script to add the area by basically asking ChatGPT to help us. This can be a straightforward exercise, and we can try it ourselves. So basically we can ask ChatGPT. Here we are not talking about any knowledge that you have on Python. All you need to have is access to ChatGPT. So you will see me uploading this full script to ChatGPT and then prompt it to add some features to that. Perhaps this is something we can do, and we can also ask ChatGPT to change the file name every time it gives you something on that. So yep. So this is the this Python script. In the next script, we will resolve this problem, but now it's dynamic, which is going to be quite exciting exercise. So I will see you in the next video. Enjoy.